Let's look at this power problem. It says, suppose a restaurant is opening a new location and they believe the average number of steaks they sell at any given location is 50 with a standard deviation of 21. Now notice that's a pretty big standard deviation because they have a lot of variation going on. It might also help you see it's probably not a normal distribution because I really can't go 3 standard deviations above and below the mean. Fortunately, I have a decent sized sample, so I'm probably going to be in good shape, although we don't normally or typically check the conditions on power problems. They really still apply. It says they aren't sure if this local restaurant is the same or if it's different than the others. So they took a sample of 36 days and used an alpha level of 5%. Step 1 is to set up the hypotheses. So HO is that this restaurant is just like the other restaurants, where mu is the average number of steaks sold each day. And they're not sure if this restaurant is different, so the alternative is the two-sided mu is not 50. Now it says here that my alpha level is 5%. That's where I'm going to set my fence. And so to find the Z star, I've got a two-sided test. So my graph is going to look like this, with each side being 0.025. So I'm going to grab, in my case, I like to use the T chart. If you use the very last row of that T chart, it's the same as the Z chart. And so I'm using the T chart where the upper tail probability is 0.025. And I'll scroll down until I see that the Z star critical value is 1.960. 1.960. So my Z star is 1.960, and it could be positive 1.960 or negative 1.960. I'll also show you how to do this on your calculator. Since I've drawn the picture and I see that the tail probability is 0.025, I could say second distributions, inverse norm of 0.025, leave those as 0 and 1, and I get that negative 1.960. Typically, critical values, the stars, are just written as the positive number, and it can be either side of that. I don't know why both of those are part A. Don't be concerned with that. Now it asks me to unstandardize the fences, if you will. In this case, there's 2 fences. If it was a one-sided test, if this part right here had only been a less than or a greater than, then I would only have 1 fence. But in this case, I have 2 fences. So I'm going to take these 2 numbers, negative 1.960 and 1.960, and I'm going to unstandardize them. So you can grab your calculator and work those problems out. And I get that the fence on the left is 43.14, and the one on the right is 50.86. Part C, standalone problem, the probability of type 1 error. This is alpha. This is 0.05. No work to be shown there. It's simply a matter of paying attention to that. Another way of stating that is a significance level of 5% means the same thing. So now to the next part. It says draw a picture and find the probability of a type 2 error. So I'm going to start at the beginning again. I've got a curve that looks like this. The middle of this curve is 50. The standard deviation is 21 divided by the square root of 36. I've got a fence here and here. Inside these fences, I fail to reject HO. Outside the fence, I reject HO. we discovered that the critical values here were negative 1.96 and 1.96. That's in terms of Z. But back in terms of stakes, these numbers were 43.14 and 50.86. So now they have asked me, what if the new mu that I'll draw in blue, this new blue mu is 40. So that's down here to the left of that left fence, and it's going to look like this. And really, I'll keep drawing it because we know it goes on actually forever and ever. And this fence is centered at 40. And this is where the bulk of the work is here. A type 2 error is beta, the probability of a type 2 error. The probability that I fail to reject HO when 40 is true and not 50. So beta is this area here. It's the area inside my fences where I fail to reject HO. So beta is the probability that I get an X bar between 43.14 and 50.86. So I need to standardize these numbers right here. So I'm going to standardize them according to my new blue mu, 43.14 minus 40 divided by 21 over the square root of 36. Z 50.86 minus 40 over 21 divided by the square root of 36. And I'm going to do this on my calculator here. So 43.14 minus 40. And I have saved that standard deviation to make it a little easier. This is 0.897. It makes sense to me that it's a positive number because that fence is to the right of my blue mu. And this one is 3.103. I'm a little more tolerant as a teacher of round-off error in these problems because there's quite a bit going on. You should be careful about round-off, but it's not the biggest issue that I want to face right now. And so now I've got to find the area between these two curves. Now the way that I do that I prefer my calculator here, but I'll show you both of them. So on my calculator, I'm going to say normal CDF of 0.897 to 3.103. Paste, chicka chicka whir whir. So that area is 0.1839. Let me also show you how to do this on the chart. Got to pull up a chart real quick. Let's see. Okay, the first number was 0.897. That'll round to 0.90. 0.90. So I look on this chart for 0.90, and it's right. Zoom in a bit more. It's right here, 0.90. That's 8159. 8159 is to the left. 8159. Let me remember that. 0.8159. And the other number was 3.10. So again on my chart, 3.10 is right here, 0.9990. 0.9990. When I subtract those two numbers, .1831, essentially the same thing. Like I said, there's a little round off error because the chart's not as precise and I've been a little lazy perhaps with some digits in my work, but essentially the same thing. In fact, I would say that's about 18%. The probability of a type 2 error is 18%. Again, here's what that means. If I took lots and lots of samples of size 36, when the truth was 40, but I thought the truth was 50, 18% of those samples would fall in an area that permitted me to keep believing 50, thereby making a type 2 error. I'm going to just call this 18% for the rest of the problem. So the next part says, what's the power of the test? Well, the power of the test is 1 minus beta, so it's 1 minus 18% or 82%. Back to my graph again. That's the area outside my fences. That's the area out here with a tiny little bit over here also. And this area, this purple power region, is where I reject HO correctly because 40 is true. That's power. Power is a good thing. This is a bit of a judgment call. This is not bad power, so I'd say maybe it's fairly high. The best way to improve the power is take a larger sample. And that's the way we'd like to recommend getting better power, is with a bigger sample.